Hello, everybody, to the fourth Astronomy in Context video, where we are going to take a closer look at parallax, specifically stellar parallax, which is the astronomer's version of determining the distances to the stars. And what we're going to do is to look at how this simple concept, which we recently learned in class, can be used to map out the Milky Way galaxy that we live in, so we can understand that we live in a spiral Milky Way galaxy that has 200 to 400 billion stars and is flat disc shaped that has spiral arms, two major spiral arms, and several smaller spiral arms, that we are about a third of the way from our galactic core, and that our galaxy is about 100,000 light years away. How can we determine all of that? Really comes down to something simple that we've all learned: parallax. So let's quickly review what parallax is. So bear with me, you probably did this, or hopefully you did this whenever you watched the class video. Take your arm, stick it out at arm's length, stick your thumb up, and now close your left eye and sight something up. Have your thumb cover up something on the wall some distance away from you. All right, so now that you have where you can cover up something on your wall, looking from your right eye, switch from your right eye to your left eye. One vantage point to another. Now from the left eye vantage point, back to the right eye, left eye, right eye, left eye. What you'll notice is that your thumb appears to be shifting in position with respect to the background, with respect to the wall. So that apparent shift with respect to a background, when viewing something from two different vantage points, your right eye versus your left eye, separated by some distance that we call a baseline, the distance between my eyes, we call that parallax. When we apply that to the stars, using the baseline of Earth's orbit itself to do one measurement at one point in its orbit, wait 6 months for it to go halfway around its orbit, and then taking another image of a star, we can see that parallax, that shift, just like you saw with your thumb, back and forth for a foreground star against very, very, very distant stars. So we can measure the parallax of the stars. But what I want to convince you is that parallax is connected to distance. Because if I can convince you that parallax is connected to distance, then you will know that we can use parallax to measure distance. We can leverage that dependency of parallax on distance to actually determine the distances to the stars. All right, so I'm going to go through a brief demonstration. So here I just have a upright stick against a background, and I'm going to use my meter stick taped against the wall as my background, and I'm going to move my computer camera from one vantage point to one that's 20 centimeters this direction. And I want you to pay attention to how the stick moves with respect to the meter stick on the wall. So here we go. I'm going to move it 20 centimeters. And you can see that it appears somewhere else with respect to the background. It has shifted its position with respect to the background. You just observe parallax. Now let's shift back and forth. So you are observing parallax in real time right now. Now where the stick appears, according to the background, appears to be in different places when compared to the background and viewed from two different vantage points. Now, the distance part, I'm going to move this to be about 3 times farther away. So now it's about 3 times farther away from the camera than it was before. So if my understanding that parallax and distance are inversely proportional to one another, another kind of fun buzz thing, what that is really telling me is that the distance has tripled, 3 times farther away, which means that the shift back and forth, the measured parallax, should be 1/3 as large, 3 times smaller. All right, so we expect smaller parallax. Let's repeat it. So 20 centimeters to the right, 20 centimeters to the left. You can see the parallax is smaller, and it's about 1/3 what it was before. So confirmed, parallax becomes smaller with distance. Now let's think about the distance to the stars themselves. Sure, we're using a really, really big baseline, which makes that shift appear bigger. Notice that if I shift this, here's 20 centimeters. If I keep going, it just gets bigger. And going back, and I'll push past 20 centimeters. So a bigger baseline, a bigger shift. So whenever we measure this for the stars, we're using the baseline of the Earth. But this thing is only like 60 inches away from the camera. The stars are light years away, tens of light years, hundreds of light years, thousands of light years away. Just to the other side of the galaxy is 100,000 light years away. So that shift back and forth, imagine if you were to hold your thumb out to be a light year away and blink your eyes back and forth. It wouldn't shift very much, even if you made a baseline the size of Earth's orbit itself. And that's the hard part, is measuring that really small parallax. It wasn't done successfully until 1855, I think that's the right year, by Bessel, that measured the first parallax of the stars. And since then, we've gone a little bit crazy with it because it allows us to build a map of the Milky Way Galaxy. Okay, now that we know what parallax is, let's jump in. And I want to show you some visuals and end with a video of where we currently are, because I want you to understand how parallax, a simple concept, allows us to understand the Milky Way Galaxy, which is a challenge because here we are on the Earth that's in orbit around the sun. So we're moving constantly around the sun. The sun is just one of a few 100 billion stars in the Milky Way Galaxy that's orbiting the center of the Milky Way Galaxy. So you got the sun going around the core of the Milky Way Galaxy. You've got the Earth going around the sun. And here we are just on this little tiny planet with all those other motions going on, looking out into the Milky Way Galaxy. How can we be inside the Milky Way Galaxy and build a map of the Milky Way Galaxy? The key to that is if we know the positions of all the stars, what direction they are in and how far away they are, then we can build a literal map of the Milky Way Galaxy while staying inside of it. So we can take a view like this, where you can see the Milky Way Galaxy here, and we can see all the other stars as well and figure out how far away they are and where they are and build a map. So this is the map, the current map of the Milky Way Galaxy. This is not it does not have all 2 to 400 billion. Notice we don't even know the total number of stars. 2 to 400 billion is a pretty big range. But this is an artist's conception based on real data of what the Milky Way Galaxy looks like, our best current model of the Milky Way Galaxy. So you can see that we can tell a lot. We can see that we're disc-shaped, we're flat, we are a spiral galaxy, so we've got these spiral arms where you see denser clusters of gas, dust, and stars, which are the part that we're mapping out. We can see that there's a core to the galaxy in the direction of Sagittarius. And if you look towards Sagittarius, then you're looking around right here towards the core of the Milky Way Galaxy. Notice that the Milky Way Galaxy is also going to be flat and disc-shaped, and we can tell that because if we look, here is a thin streak through the sky. We are looking from here, from the sun, towards the center of the Milky Way, and this disk is pretty thin, so it appears like a thin streak through the sky, angled by about 60 degrees, because that's the orientation of our solar system with respect to the galactic plane. Already telling out some pretty cool stuff, but I haven't had to use distance yet. Where does the sun lie on this? Well, we're right here in the Orion Spur. Some people consider it an arm of the Milky Way Galaxy. Some people consider it a sub-arm of the Milky Way Galaxy. But we are about 30,000 light years from the center of the Milky Way Galaxy, and we got another 30-ish plus thousand light years to go to get out of the Milky Way Galaxy, because the entire Milky Way Galaxy from side to side, its diameter is about 100,000 light years across. To use this in the determining distance via parallax units, the parsec, that's about 30,000 parsecs or 30 kiloparsecs across. So how do we know this? Parallax. If we can map out the positions of the stars, then we can build a map like this. And that has been a task that astronomers have been working on for a long time. Early on, we didn't know a good method to determine the distances. We had to make assumptions like all stars are the same brightness, which is not true. And then William and Caroline Herschel built a rudimentary map of the Milky Way Galaxy to realize that it's kind of flat. But it wasn't a very great map. And slowly, over time, as parallax became used more and more, we started to build a true map of the Milky Way Galaxy. And that's what I want to show you, is how we can actually tell that this is what the Milky Way Galaxy looks like. So here again is the same model that we had on the left before. And on the right, now we're viewing an edge on. So you can see that the disk is thin. We have this bulge in the center, the galactic bulge, where contained within the heart of the Milky Way galaxy, we have a supermassive black hole. All large galaxies have a supermassive black hole. And then we have a halo where some stars live, but mostly those stars are in globular clusters. So we have a disk, we got a halo, we got a core, got the bulge, we got a bar. How do we determine all this? Well, we really need to know the positions of the stars. Enter the most modern mission to determine the positions of the stars, the European Space Agency's ESA Gaia satellite, the successor to the Hipparcos satellite. Hipparcos measured the positions of stars with a high degree of accuracy for about 100,000 of them. The Gaia satellite is going for billions. We've already mapped the positions of about 1.8 billion stars, and it has the sensitivity to do that out to like 50,000 light years away. That's almost across the Milky Way galaxy, but not quite. So no, we can't build a full map of the Milky Way galaxy yet because we cannot measure parallax to things that are more than 50,000 parsecs away. We have to be clever and use other distance measurements which hinge upon the parallax measurements to determine distance. But they are out there. It's called the cosmic distance ladder. But it all rests on being able to determine the positions of the stars. So not only is Gaia measuring the positions of billions of stars using stellar parallax, it's also measuring their motion, how they're moving. And if we know their motion and how they're moving, not only can we build a map, we can make it dynamic and see how it changes with time. So let's go ahead and give you some current statistics. Where is our current map of the Milky Way galaxy before we hop into a tour of the latest Gaia data release? So right now we're in data release 3, or the early data release. The official data release is not out yet. The early data release was released December 20th, 2020, so very recently. And this is just sort of a summary. So it's measured the stellar positions via stellar parallax for 1.8 billion stars. It's measured the position via parallax with motion for about 1.5 billion stars, which allows us to really start building maps like this that are going away from this is what we think it looks like. We know the spiral arms are here, and we can replace those with actual data points. And if we know the positions and how they're moving, we could send that into the past or send that into the future using models that account for gravity and how things interact with one another. Actually understand how the Milky Way galaxy used to look and how it'll look in the future and how it's interacted with things, or find evidence of things it's interacted with in the past, based on things like we see the Milky Way is not flat like a disk perfectly, it had a little bit of a warp to it. But what I really want to show you is a map of the Milky Way galaxy from the Gaia satellite that's using stellar parallax. So actually, just in case there's sound, can't remember if there's sound, I'm going to reshare my screen, but turn the sound on. And what this is taking the positions and the motions of about 300,000 of our nearest neighboring stars and building a map of the Milky Way galaxy. So what we're about to view, well, yes, it is generated by a computer, all the graphics are. What we are looking at is based on the real positions and the real motions of hundreds of thousands of stars. This is a real fly-through of the real positions. So each one of these stars represents a real star with its correct location. Keep that in mind as we watch. I guess it does not have sound. So in the next one, I'll show you all the stars within 100 parsecs, how they're going to change over the next couple million, 10 million years or so. So remember, all of these stars, they're not just, oh, let's just put a star there. They are really there. This is the map. All unlocked because of stellar parallax. Look at that, 331,312 stars. They're actually putting the real colors. If you take Astronomy 152, we go into what the meaning of the color of stars are. We'll hit a little bit of that in Unit 1, Part 4, when we study light itself. Now you can see the velocity vectors. So that's showing what direction they're moving, and the length of the arrow showing how fast they're moving in that direction. So we have a map of all of those stars and know how they're moving with high degrees of accuracy and a large amount of precision, which allows us to do some pretty incredible studies of the galaxy that we live in. I just love this part right here. We're going to go look at binary stars. So about 50% of all stars are in binary systems, two stars that orbit around one another. And it's no surprise, it comes out in the data as well, that these things are co-moving. So their overall velocity vectors through the Milky Way Galaxy point in the same direction. Still can't believe these are real positions of stars. It's incredible. Now let's go to a star cluster. These are regions in space where all of these stars were formed at the same time, the same place, out of the same cluster of gas and dust. The Hyades is in the constellation Taurus, right between the horns of Taurus. And since they all formed out of the same cloud of gas and dust, they're all moving with the same motion through the Milky Way Galaxy. So we can use this to identify that all of those stars are members of that star clusters. They are stellar siblings. Head to another cluster of stars, highlighting the members in yellow. And again, you can see their motions. All right, so there's our map of the stars, the 300,000 stars within 100 parsecs. Let's see how much we've mapped, how much of a map of the Milky Way Galaxy that really was, though. So that yellow blob is the 100 parsec sphere. There's our Milky Way Galaxy. Oh, it's just such a small little dot. And notice that the catalog currently goes out to about 2 billion stars, but just wow, wow. It's just simply incredible. Okay, so now let's take a subset of those stars within 100 parsecs, about 75,000 of them, and use those velocity vectors and some physics of knowing how things orbit with masses, some that we're going to be talking about soon, how things move in response to gravity, and gravity is created by mass, really the warping of space-time. But let's just see how stars will move around in the Milky Way Galaxy into the future using real data. So there's our 100 parsec sphere again. And now it's going to take 75,000 of those stars and evolve them, see where they're going to go for the next 500 million years, how they make their way around the Milky Way Galaxy. It takes about 220 million years for a complete orbit at the sun's distance. All of this not possible if we cannot use stellar parallax to figure out where those stars were and how they were moving with a high degree of accuracy and precision. If we don't know where they are, then it's hard to build this. If we don't know how they're moving very well, then all of this would change. They'd be very sensitive to those errors. And here you can see this from data sets like this and modelings like this, where you can start to understand why we have a warp. Although the warp probably comes from a cannibalization of a satellite galaxy. So the Milky Way ate one of its satellite galaxies about 6 billion years ago in the past, leaving a warp in our disk. Okay, so we went from a simple in the living room demonstration all the way to understanding how we build a map of the Milky Way Galaxy and looking at the best current map of just our local region of space in the Milky Way Galaxy. So this little concept that we learned about stellar parallax and its ability to tell distances becomes one of the most powerful tools in all of astronomy. And I really hope that this gives you a little bit of an anchor, a little bit of context for that weird lesson that we learned about stellar parallax. Thank you for tuning in. I hope you enjoyed the video.